Oh. So, graded your exams, you have your grades, and you can pick them up after class. I would say those of you that receive lower grades, part of it is you did not pay attention or you were not focused. It was not that you didn't know. I could tell from the kind of mistake you made. All right, so it's like exam taking skills, right? You have to be focused for 55 minutes and always leave 10 minutes or 5 minutes to review things. So I would say the lower grade doesn't necessarily mean you didn't understand. All right. So a couple of things that we have today. I actually populated today and tomorrow, Friday's lecture, and I think I put the annotated version as well for the other one. Yeah. Okay. So I would start with today's lecture, which is frequency domain, very quickly, just to remind you what frequency domains are. Most of you know. So this is just basically a reminder. And then on Friday, I will talk about things that are related to this class. On Friday, we are also going to use MATLAB to solve design problems. So if you have to stay home and use your MATLAB, you can attend through Zoom. You still have to attend through Zoom. If you want to be here, I'll be here. Make sure you have the toolbox, things are working, and you can follow along because it's the same. I will be talking about things on MATLAB and you need to follow. So I posted the lectures beforehand, so you can at least review and to see what we need. So you can at least check the commands and see if your MATLAB runs. All right, so on Friday, you will open your MATLAB before you attend the class. All right. And then after frequency, I'll talk about homework 5. And after that, I'll go back to the example of Monday lecture that you were supposed to review those couple of slides, right? So today's class will be very light. I also posted a cheat sheet for all MATLAB commands. I don't know if you have seen it or not. Here, useful MATLAB cheat sheet. You can keep it handy when you're coding. I try to put as much as I thought it will be useful. We talked about most of them. One of the commands I'll talk on Friday, which is rlook find. Other than that, everything is there. So if you use a command that's useful for you and you think the class can benefit from it, you can put on Discord. I will update this page. Okay, me or Brad, we can update this. So put more command so you can always use that. You can print it and keep it for your next classes or for future also. And that will be mostly using control, solving control problems, basically. All right. This is the homework. Frequency. All right. Why is my face there? What happened? I don't always have my face there, do I? Oh, you have to see me twice. I don't know how to take it off. All right. So, so far we learned about 2 domains, right? Time domain and frequency domain. And if you remember that we have another domain that we could go between them. So time domain to Laplace domain. And we also talked about our frequency domain very lightly. So these 3 domains are connected and you can go from one to another. So depending on what your system is and what are your requirements, you want to choose proper domain to solve that. You can always translate your solution to different domains. Why is that important? If you want to know the response of a system in real life, like position, velocity, you better solve things in time domain. Or if you solved it in S domain, convert those in time domain so you can understand what a specific answer is. If you're dealing with devices that different frequency of your input signal is important, and then you want to know the frequency response of that, then you want to go to frequency domain. So S domain is kind of a bridge, right? So it's easy to solve things in S domain because it uses mostly algebra. And the other two domains are more complicated, but once we solve things, we can just move it to those two and see what's the interpretation of that. All right. And S is equals to J omega, right? That's the imaginary part of a signal or a response. So for frequency response, we call it FRF, frequency response function. And I'm sure that you're all familiar with frequency as well. Now, we're going to take a quick look at the definition of LTI system. So if you remember, for LTI system, we can have an input, we get an output. Now, if we have different LTIs, we can add up all of our inputs, and then we will get the addition of all the outputs as if they were separately applied to our LTI system, right? The proposition. So same thing holds if we go to frequency domain. It doesn't matter. It's the same thing. Now, in frequency domain, we also have a steady state. And the difference is when we are using our, when we want to look at the frequency response, instead of giving a step function, we're going to give a sine wave, sinusoidal, so the sine or cosine. And the reason is that in frequency domain, the magnitude and phase are important for us. So we're going to give an input that has both of this in it, right? So let's solve an example that has sine domain as an input and see what happens in the output. So if your input example is, so I'm going to introduce my LTI system. Let's say this is your LTI system. So this is input, this is output. Plus. So whatever system that can go in there, right? Now, if your input is something like sine of 0.5 t, okay, so this means that your omega, so it's omega t, right, is 0.5 radian per second. Can you find your output? Can you find an expression for output? It can be in time domain. Do you remember how to write an equation from block diagram? Do that. Write the output for me. That's 2. That's gain. So every time we have this guy is a gain. The other one is 1 over S is our integral block. You can just write the time domain representation. You don't have to put it like that. This is the takeoff point. These two signals are the same. If this is input, this is still input, this is still input, right? So what do you have here? 2 times the input. Plus, if we go from the bottom, the integral of the input, that would be your output. So the output would be 2 times sine of 0.5 t plus the integral of our input. So I'm writing it in time domain, right? Otherwise, I have to convert sine to Laplace, then 1 over s. I'm not doing that. Sine of 0.5 t dt. Now, this becomes, if you take that integral, 2 sine of 0.5 t negative 1/2 or 0.5 cosine of 0.5 t, is just omega t, right? Now, this is our output signal. So why did I put it here? Because since this is LTI system, if we give it a sine wave, we always have to we can get an output in the form of sine wave, sinusoidal, and then we can use that for all the LTI system, right? So if you remember from trigonometry, it's like, nice one, Dr. Z. Some of you might remember, a sine of x plus b cosine of x. Do you remember what this is equal to? I don't expect you to remember. I did not remember, I had to look it up. So x b plus a tangent. This is a plus, that's a t. So a tan b over a. Right? Now this is more familiar. So this we will call it magnitude. This we'll call it phase. And this is that omega that we had there, right? So if we write our signal to that form, so square root of a squared plus b squared, we get 2.83 sine of 0.5 t. So our omega stays the same. The LTI system, it does not, yes.
Is that a 2 instead of 1/2?
This is 1/2, it comes out.
Yeah, right. 1 over 0.
Oh, no, it is, doesn't matter. That was not the point. -2. All right, cosine of sine of 0.5 t. I need to check this, but whatever. Minus 0.785. This is in radian, right? So if this is our magnitude, this is an important point here. So this is our magnitude. This one, our phase, we will write it in degree. Why? I don't know. That's how in Bode plots we plot it. And even though you always find radian, you convert to degree. And I think it's easy to imagine degrees than in radian. So I would say it's mostly for like to visualization. There's no difference. All right, so we get our magnitude and phase. So our magnitude in a frequency domain is always going to be a square root of a squared plus b squared, and our phase is going to be a tangent of b over a. We're going to use that and carry it everywhere we are doing our calculation. All right. So a couple of just reviews and reminders. The meaning of magnitude and phase. Magnitude, the amount of input signal that is amplified, right? So if you have input sinusoidal goes to an LTI system, you will have something that could be amplified. That amplification is your magnitude, right? Now, it could be amplified greater than 1 or less than 1. We don't know. It's just a K that is amplified by. Your phase is the shift in phase, which is in time lag, basically, between the input and the output. So if you have the peak of your input and to the peak of your output, that will be your tau, the time delay. All right. We also have our phase lag. Phase lag is omega times that tau. That would be our phase lag. So omega is the frequency of that signal that goes input. So for LTI, that omega stays the same, does not change. So if you have input omega 1, the output of that one signal is still omega 1. No, but you could have different sinusoidal going to an LTI system. All right. Frequency response function, we will write our response in terms of magnitude, sinusoid, omega t plus our phase. If you remember from your previous courses, your magnitude is going to be, so h is your transfer function, h of j omega. So the magnitude of that, and j omega is your s, right? So h of s, put j omega instead of s, you have the omega, and then you get the magnitude from there. For phase is just the angle between numerator denominator, or you can say a tangent of b over a, which is the same thing. If we say negative phase, it's just the output is delayed. If you have the magnitude if you have magnitude volt per volt, to get it in dB, you will write 20 log of that magnitude in the base of 10. The other way around, if you have in dB and you wanted volt per volt, you use m is 10 to the power of dB over 20. Now, question. I said volt per volt, right? Is it always volt per volt, the transfer function? No. So pay attention what your transfer function is. So if it is a voltage transfer function, you have volt per volt, right? If it's a current transfer function or impedance transfer function, then your values are, your units are different. So it would be, for example, impedance to impedance, which is 1, right? We just say it so we can identify. But when we go to dB, it's just dB. That's just a number in decibel. All right. It is important because you want to identify your system and you want to know what is it that you're looking for. Because you could have a DC motor, you could find different things from it. You really need to know which transfer function to drive. Body plot, how many of you have seen body plot? Raise your hand. Amber, you haven't seen body plot? Jujian, you haven't seen body plot? That. Have you seen that before? No? Okay, good. At least one person, so I can go over it. So body plot, you usually get 3 plots if you just, you get 2 plots, sorry. One is your magnitude, the other one is your phase. So basically, remember we found the response that was magnitude sinusoid omega t plus phase. If you change the omega from 0 to infinity, you get different responses, different values. If you plot them all, it becomes your body plot. All right. Now, the first one, the magnitude is basically gain of, we can find the gain, which is the output over input. And for the phase, it's just a lag time, your output to the input lag time. All right. If you click anywhere on body plot, you can find your system, whatever your system is, what frequency, and then what's the value. This is really good because we are interested in a few points in a body plot. So MATLAB plots it for us, so we don't have to do it, but we need to be able to interpret that plot. All right, so how many of you know how to draw a body plot in MATLAB? Raise your hand. How'd you draw it, Matthew? It's just Bode command. Did you know Bode is from the Ohio State? Yes, be proud of it. So you should be really good at Bode plot. Yeah, dang, right. It is. I was very excited that when I figured it out. So you build your system however you want. Your favorite method of creating system, numerator, denominator. You can have pole 0, ZPK, or you can have TF of S. Build your system, then body of that system. If you have grid on, you see all the dashed lines, and it will plot both of it for you. All right. So for your class participation, it's due on Friday by class time because we're going to use MATLAB. I just asked you to draw a bunch of body plots, and I want you to look at it. Look at the transfer function, look at the poles, look at the zeros, and check how the body plot is changing. So become familiar with the change from S domain to frequency domain. Okay, we can get a lot of information from a body plot, how many poles a system has, how many zero it has. It's not just cutoff frequency and gain. That's like what we know quickly from body plot, right? We can tell if it's a stable or unstable system. from the body plot as well. So when you're doing your class participation, look more in detail, like, oh, what if because I've given you, for example, 1 over S plus A. I let you pick A. For example, A is 3. So 1 over S plus 3, the system should be stable, right? Plot the body plot, how does it look like? I would also draw 1 over S minus 3 for an unstable system because I know pole is on the right-hand side, and check the body plot, see how it changes. All right, so it's on you to understand moving from S domain to frequency domain, all right? And we know that magic number here, -3 dB, is, so we're gonna call it bandwidth frequency at -3 dB is not -3 below the maximum gain, is -3 dB, period. All right, so it's half power point if you remember from 2020. Is the point that if we are if you are designing a filter, after that we don't care what happens, right? So, good on this? Awesome. All right, so the last thing here that I want to show you is how to relate to response of a step response of a system to body plot. So if you have a system, you apply a step function to it, you will get the plot on your left, right? So it could be 3 cases. You can have critically damped, under damped, over damped. And you can tell from the shape, I know because it was your exam, most of you answered correctly, right? Now, for the same system, if we plot body plot, is going to apply a sinusoidal to the same system, is LTI, right? If it's stable, it has to remain stable, doesn't matter what we apply to it. So it will apply a sinusoidal to it and shows us how the frequencies are changing. You can relate the 2 systems. So you're well familiar with that one. I plotted the same system, but just the body part. So the red one is your under damped. Over there, you see that under damped you had overshoot, and then after a while you get to steady state, right? From the body plot, you're going to have a peak in the magnitude, and you're going to have a dip in the phase plot. So if you see that, it's still stable, could be stable, but at least the shape of it will tell you which case in time domain. And if you go back to S domain, it has maybe some pole closer to imaginary axis because there's a little bit of overshoot on there, right? Then you have critically damped and over damped. So we usually want to be around critically damped if possible. That's our ideal response. But if you are over damped, you might have some steady state error with the damper system too much, right? So the other thing I want you to pay attention is how these two relate. So you're well versed on that one. I want you to be same with this one. So if I show you different body plots, you should tell me which could it be. All right. So think about last question of your exam. So it kind of for everyone was the same. You could tell me which response is for which transfer function, right? So this is the end of the lecture on frequency. And as you saw, it's just for review because you're going to use these information on Friday at the beginning. I'm going to go over how do we now understand if systems is stable or not. Where should we look at? When you're doing your class participation, include should not make you come to class because of that password. Well, that's my only way to bring you to the class, because if I tell you it's good for you, it's like vegetable. You're not going to eat it, right? If I make a nice smoothie and give it to you, you eat, you drink it. So that's like that smoothie thing. So I'm doing it because I know it's good for you, but if it was on you, you might not be here. You know, there's always a push needed for everyone. So let me, how do I get out of this? Stop sharing. Okay, we're gonna stop sharing and I'm gonna have you screen sharing. So you can take a minute. How do I get me out of here? How do I get rid of myself?
I think when we can.
Oh. Oh, well, I'm there. Speaker view. All right, so the next thing I want to share with you is homework 5. How many of you looked at homework 5? Okay, I want the rest of you look at homework 5. Because I'm not gonna help you after this. So it's a good time for you to look over. I'm there the whole time. Screen, broadcast. All right. Ignore me there. All right, so a couple of things. This homework, you cannot use any of your classmates' help. So no Discord business or outside of Discord business. All right. This is the accumulation of everything you have learned so far. Trust yourself, you can do this. It's not hard. You just have to pay attention and it's accessible. You can come to me and Brett only for brainstorming. So say, hey, I'm designing my controller. I don't exactly know what to do here. Like, and then you offer a few things and then we try to guide you. All right. So this is, imagine this is a real life project. So I chose a DC motor. So most of the devices you will see, if it's not purely like PLC or like electronic, they have some sort of actuation in it. So you will deal with mechanical components, right? So we call them electromechanical, but because there's an electrical system and there's a mechanical system connect to it. So imagine a robot arm, right? It has an actuator as a joint, and then the rest of the mechanical system, so the actuator has electrical side, and this mechanical side is the load on the motor, right? So the load usually is the mechanical side, and the device itself has electrical circuit. We separately solve both of these problems, right? Writing differential equation and then convert to transfer function to see the step response, for example. All right. So here you have both of them next to each other. Your approach, whenever you have two systems like this, is that you look at them first separately, find where they are connected, and then identify, for example, from the load, is it the force, is it the torque that is applied on the electrical side, and from the electrical side, what is it applied to mechanical? So there's always one point that they are connected, right? So a couple of definition on this. So I simplified that so to an RL circuit and a rotary disc for the motor. So we are modeling, right? We're simplifying. On the electrical side, you have voltage source V, a resistor and an inductor, and then you have your back EMF, the voltage part, the part that the load can be measured from the mechanical side, right? And then on the mechanical side, you have a disc. So this is rotational motion. So there's going to be inertia involved. The position is theta. The velocity is theta dot, or the speed, right? Theta, the rate of change of theta. And the point that these two are connected can be found using tau of M, which is KT times IA. So you see IA comes from the electrical side, and tau is a torque, is a load applied to the motor side, the mechanical side. And then VB, which is KE times theta dot M, the speed, how fast the motor is rotating, is going to be important for the electrical part. That's the two equation you need when you are dealing with electromechanical system to connect them together. Now, how do we go about solving this? How do we drive the transfer function for this? I put all the information that what each of those are, all right? But how would you approach this problem? Here, so reminding you again, this was our system. I'm going to identify the electrical part and mechanical part separately, all right? That should give you an idea. So we knew that this is going to be VB, which is KE theta dot M, right? And the mechanical side, that's not. On the mechanical side, we have tau M. Here, I'm going to write tau M, JM, theta M, they're all M. Because of that M I put here. So that's your tau M. Then you have so you have a friction in there or damping, whatever that is. It's modeled, so it could be damping and friction all together modeled in one. And then this is your J. This is the inertia. So, and we know tau M is KT, case of T, IA. So you see this point that they are interfacing, right? So they have one from the other one. So this is, we separated our electrical, mechanical system, and then we also identified the point that they're interacting. So there's always one factor from the other one. So now how do we go from here? What is your homework asking? Homework 5. I don't know, what is question 5, homework 5 saying?
Oh. The whole problem? Or
The whole problem.
the common actuator and control system.
Okay, don't read it. Read it by yourself. Tell me what do you think is asking you to do.
Develop a system transfer function.
Okay, that's one thing, right? So you have to develop the system transfer function. Then what you do next?
Not a controller that satisfies the requirement.
So you have a system, you have some requirement that you need to satisfy. The first thing, you need a transfer function. Then you get probably like a step and see what is the response currently and compare it to your specification. If it did not meet, you design a controller. What kind of controller do you design? Your pick, I don't know, whatever you think. And all of them are right as long as you find the proper coefficient. So PID, pole placement, lead, lag, anything you want. You can even design 2 controllers. And both should like meet the requirement, like if you want to go the extra mile, but you don't need to. All right. And then I'm asking about good locus, response for before and after kind of thing, right? So first, it all comes back to what's the transfer function? Now, how do we develop a transfer function from this? If this was separate systems, what would you do?
What do you do with the equivalent values? Like the unit, does it get right over the
We need to find differential equation. So you write differential equation for each of them, right? We'll still do that. So how do we write differential equation for electrical systems? Let's say maybe get a KCL, KVL. I don't know. Find differential equation. How do you write differential equation in DiffEq? 1. And then for mechanical system, how do you get the differential equation? That's the free body diagram, right? And then there's Newton law of force, or the other one, which now is the other one because it's a rotational system, right? Free body diagram. So from FBD and Newton law, find diff EQ2. This gives you two ODEs, right? In time domain. Correct? We have done example of both of them. So you can write it and check lecture, previous lectures is in the exam one part, and make sure that you write them correctly. It's in time domain. Now, transfer function is in S domain. How do we change? So we have x goes to s, x dot is s, x of s, x double dot is s squared, x of s, right? So from time domain, go to S domain. You still have two equations, two sets of equation, right? Now, what do we do from here? So we have two sets of equation in S domain. We still need to write transfer function. Do you remember you had like system of mass, the card system, that there are two cards connected to each other, and then from there you could write transfer function? Is the same scenario, just the variables are different, like L of S or something like that. Now, piggyback to what I talked about, volt per volt transfer function, or impedance to impedance transfer function. For the same system, you could have different transfer functions, right? Now, how do you know what are you trying to find? You go back to your question. Find, identify system output, system input. This means that what is it that we are trying to control? That's the output, right? And the input is here step response, because that's what you're trying to do. So the transfer function would be the output. After you know what are you trying to find from that S domain, your transfer function is going to be your Y over your R of S, your input. I just put R of S. So that Y is basically important to find out. Okay, you could be controlling many things. You need to know what you're controlling. And I can't tell you because that will solve 50% of the problem. All right. From there, then you have a transfer function, step response, and all those beautiful things we did. Check what needs to be changed. You need the requirements. And if there, so what are requirements? Can you read that here? So it says only time less than 2 seconds. You could have overshoot of 5%, right? So don't go for overshoot of 0 or try to eliminate overshoot. If it got eliminated, fine. But you don't have to drive that. Once you design your controller, you plot everything, then you come to my office for interview, right? So if you have like 200, like 2,536 for your KP, well, I'm gonna ask you, why is this so large? Right? How much do you think you have to spend to buy that motor? Because that's literally the motor, you have the current, is gonna smoke it. So once everything is on the paper, take a look back and look at your numbers. Does this make sense in real world? From there, if you need to go and say, hey, let's just check internet, think what people say, like, you know, if we are doing like KP or KR of this, what kind of voltage or current translate to? Okay, so that part, those questions I'll ask you in interview, just to show understanding. The transfer function should not be difficult. You've done it before. And I know like some of you will check internet for that. I will ask you a question to see if you understood what happened. All right, so if you can check things, but you need to understand what happened. All right, so that's a fair game. The interview would be 15 minutes, so I will see all the submissions and then I will find questions I'm going to ask. So when you come in, you probably start to go over it quickly and start answering questions. All right, like a job interview. All right, any questions here? No question? No? what time is it? Let me do this, go here before it yells at me. So this part, you can just even not pay attention. You can always go back to the video. I'm just gonna show you some body plots. I'm gonna draw body plots so we are familiar with how to draw because you're gonna use it in your class participation. So step by step, running and advancing, clear everything. Well, here, system 1 over s plus 2. I need something here, this guy. Should draw body plot for me. So that's a body plot. Grids are not on. I can say grid on and run it. There. Let's see what it was, s plus 4. Yes. That. So all you have to do in your class participation, there are a1 over s plus a. You can choose a whatever, but in your script you will have values for that a, right? So that's how you draw. You could use 0 pole. So I could say, I could run this one. That's a different way of plotting from 0 pole, creating your system with gain. There is another command. I think I didn't add it to the cheat sheet. So negative dB is when you find your bandwidth cutoff frequency, right? Let's say you so that's when the gain is at 0 dB, negative is right under. Let's say you have a maximum gain that's not 0, and you want to know what happens -3 under it, or -5 under it. So a line down. This command will help you. So you say what is your system? So the system I created above, K is DC gain system, and then you can introduce dB drop. That can be any number that you want to see what is that gain on that number. And then you use bandwidth command, and it will tell you what's going to be the bandwidth if you drop that much. So does that make sense? So if it is a passive filter, let's say low pass filter, that the maximum gain is going to be 0 dB. So if it is -3, you put -3, it gives you -3 dB bandwidth. But if you want to find something different, you can always just plug that number in there. All right. So when this will be useful, sometime when we're designing, we know that the system will be stable at such and such frequencies. And you try to see what, like, if I drop 5 dB, would it give me that frequency? So this command becomes useful. So you don't use it right now, but you might need to use it in future. So I thought I would show it right now. You could also draw something. If you want to compare, let's say, different systems. So the same system has different gain, 10, 20. So in body plot, you can say 10 times that system. You can do that in a step as well. Or if your input was A over S, right? That A is basically you're multiplying your system by that value, which was also in your exam. All right. So the same thing, if you wanted to see how the system is changing, you can use this just directly multiply inside. All right. So on Friday, this is for today. On Friday, I will give you a few tips on how to use body plot to see if a system is stable or not. What are the points of interest? Then I will go over design examples using root locus and body plot, however much time we have. All right. So those are just ongoing problems. If we didn't finish, we will do it next Friday. Okay. So we save Fridays for MATLAB from now on. However Friday we have left. Yes. You can come and get your exams and leave.